From the very first moment humans really looked up at the night sky, there's been this deep urge to understand it all. What are those lights? How do they move? What does it mean for us, down here? It's a curiosity that's literally shaped history.
It really has shaped civilizations, inspired myths, and, well, eventually gave birth to science itself.
And today, we're diving deep into that very quest, astronomy. This exploration, this deep dive into the cosmos, is built entirely on the stack of sources you, our listener, provided. Our mission, as always, is to unpack the most important insights from that material, really get to the heart of this fascinating field for you.
And we've got quite a bit to cover. We'll start with, what astronomy is fundamentally, then trace its roots way back, see how it branched out over time. We'll look at the methods astronomers actually use, and then wrap up with why it all matters, its significance.
Okay, let's unpack this then. Astronomy. It sounds so huge. Where do we even start? What exactly is it aiming for?
Right. At its absolute core, astronomy is the fundamental science that studies celestial bodies, their structure, movement, where they came from, how they develop, and not just individual bodies, but their systems, and ultimately, the universe as a whole.
The whole thing.
A whole observable thing, yes. The word itself tells you a bit. Greek, astron for star, nomos for law. The law of the stars, its ultimate goal, to really understand the origin, the structure, and the evolution of the entire cosmos.
So it's the biggest picture possible, but I guess it also involves the really small details, the nitty-gritty, like a cosmic detective story.
Exactly. A detective story playing out over billions of years. And it's very practical, too. I mean, important tasks include explaining and forecasting things like solar eclipses, lunar eclipses.
Just people would have definitely noticed.
Absolutely. Or predicting when comets will appear, or maybe more urgently, when asteroids or large meteoroids might pass close to Earth.
Right.
That has obvious implications. And it also delves into the physics inside planets, on their surfaces, in their atmospheres. That helps us understand our own Earth better.
Okay, so focusing closer to home for a second, what are the main players in our own cosmic neighborhood that astronomy looks at?
Well, you've got the 8 major planets, obviously, including Earth. Then dwarf planets like Pluto, their moons, loads of them. Asteroids, meteoroids, comets, even interplanetary dust.
Dust, really?
Oh, yes, and forms of energy fields, too. All of that, plus the sun, makes up our gravitationally bound solar system. And studying how all that moves helps us understand the solar system stability and, assess the risk of collisions with asteroids or comets. That's still a very active area.
But it's not just our backyard, is it? Astronomy's reach goes way further out.
Oh, much further. We study the sun intensely, obviously. Forecasting its activity is crucial because it affects everything from our climate to our technology.
Like solar flares knocking out satellites.
Exactly. And we study other stars to see how they evolve, which helps us understand our own sun's life cycle. Then we zoom out further, researching our galaxy, the Milky Way, and other galaxies. That helps us classify them, figure out how they evolve, pinpoint our solar system's location within the Milky Way, and even calculate probabilities like, could another star pass close to our sun? Or could we pass through a giant interstellar gas cloud?
Wow. So when astronomers use the word universe, what does that term technically cover? Is it literally everything?
That's a good question. Technically, universe refers to the entire observable region of space. Everything we can currently detect and study, all the celestial bodies and systems available to our instruments and methods right now, it's defined by what we can see in the broadest sense.
Right. Okay. Now, this is where it gets really fascinating for me. How far back does this all go, this looking up? Did ancient people really understand the stars, or was it just awe?
Oh, its roots are incredibly deep. Deep antiquity. We're talking almost as old as human consciousness. We know even very early humans observed the sky. They drew what they saw on cave walls.
No way.
Yes. And you could argue that observing the patterns in the sky actually helped shape humans as thinking beings, that initial spark of curiosity.
So it wasn't just like casual stargazing. It had a real purpose from the start.
Absolutely fundamental. As society developed, especially with agriculture, you suddenly have this critical need to track time, to create calendars.
Right, for planting, harvesting.
Precisely. People noticed the patterns, the sun's path, the moon's phases. That allowed them to define the day, the month, the year. And those calendars became deeply woven into their culture, their economy, so foundational stuff.
Can you give us some concrete examples? How did this ancient astronomy play out in daily life?
Sure. Think about ancient Egypt. The priests there could predict the Nile's annual flood, absolutely vital for their survival, based on when Sirius, the brightest star, appeared just before sunrise. That told them exactly when to do their agricultural work.
Hmm.
Or take Arabia, much hotter during the day, so a lot of activity shifted to night. So observing the moon's phases became incredibly important for daily life, for travel, for trade,
And navigation, too, I bet.
definitely, especially for seafaring cultures. Before the compass, knowing how to navigate by the stars, that was literally life or death on the open sea. They paid very close attention.
So it was practical agriculture, navigation, timekeeping, but also about building a structured understanding of their world, almost like protoscience.
Exactly right. The earliest written records we have, we're talking 3rd to 2nd millennia BCE, from Egypt, Babylon, China, India, the Americas. They all show signs of pretty sophisticated astronomical activity. And it wasn't just records. They built massive structures aligned with specific astronomical events.
Like Stonehenge.
Like Stonehenge, yes. Aligned with sunrise points on solstices and equinoxes.
Yeah.
Or Arkham in Russia. These weren't just temples, they were ancient observatories, showing a really advanced early grasp of how the heavens worked.
Okay, so from these ancient foundational observations, how did astronomy start to specialize? How did it branch out into the different fields we recognize today?
Well, like any science, as knowledge grew, it naturally specialized. Different branches focused on different questions, different methods. If we look historically, a truly scientific understanding of Earth as a celestial body really emerged in ancient Greece. I mean, think about Eratosthenes in Alexandria around 240 BCE. He calculated the size of the Earth using shadows and sun observations.
And he was pretty accurate, wasn't he?
Remarkably accurate for the time. That was a huge step, proving Earth wasn't flat. It was a sphere with a measurable size.
So what was the first major branch to really spin off from those practical needs?
The really strong drivers were trade and seafaring.
Mm-hmm.
They desperately needed better methods for orientation, for finding your latitude and longitude, for precise timekeeping.
Yeah.
This led directly to what we call practical astronomy, focused purely on those essential observational techniques. But then came a truly revolutionary shift. Copernicus. His heliocentric model, sun at the center, not Earth, laid out on the revolutions of the celestial spheres. That was the key. But, the idea of the stationary Earth was so ingrained, it took centuries for his ideas to really take hold.
Yeah, resistance was fierce. But Galileo really pushed it forward, right? Even when it was dangerous.
He absolutely did.
Yeah.
Galilei, he used one of the first telescopes, a very simple one really, and found undeniable proof. He saw mountains on the moon, so Jupiter's moons orbiting it, not Earth, a mini solar system.
That must have blown people's minds.
Completely. And his observations of Venus's phases, they only made sense if Venus orbited the sun. Game over for the old model, really. Around the same time, you had Johannes Kepler working with Tycho Brahe's incredibly precise data. Kepler focused on Mars' orbit. After just huge amounts of calculation, he came up with his 3 laws of planetary motion. Those laws became the bedrock for understanding the solar system's mechanics.
And that branch became
Celestial mechanics. It allows us to explain and calculate with amazing accuracy pretty much all the movements we see in the solar system, even in our galaxy.
And presumably the tools kept getting better, leading to more breakthroughs. It feels like technology and discovery went hand in hand.
Absolutely. Galileo's telescope was improved by Kepler, then by Huygens. Then Isaac Newton came along and invented a whole new type, the reflector telescope. These better instruments meant seeing fainter, more distant things. Not just planets, but stars. Huygens figured out Saturn's rings weren't solid, and he found its moon Titan in 1655. Later, in 1761, Lomonosov discovered Venus actually had an atmosphere and studied comets up close.
So people started comparing these different worlds.
Exactly. Scientists started comparing Earth to other planets and moons. What's similar? What's different? That led to comparative planetology, putting Earth in its cosmic context.
Okay, that makes sense. But how did they figure out what stars are actually made of? That seems like a huge leap. You can't exactly grab a sample.
Right. That's where astrophysics comes crashing in. The game changer was spectral analysis.
Spectral analysis. Breaking down light.
Pretty much. The discovery that you could analyze the light from stars to figure out their physical nature, their chemical composition, it was revolutionary. Joseph Fraunhofer, a German scientist, made detailed studies of the dark lines in the sun's spectrum. Those ones are like fingerprints.
Fingerprints of elements.
Exactly. Each element absorbs or emits light at specific wavelengths. With lab spectroscopy and quantum mechanics developing rapidly, we learned to read those stellar fingerprints. By the 1860s, this spectral analysis was the main tool for figuring out what celestial bodies are made of and what's happening physically. So astrophysics studies the physical phenomena, the chemical processes in stars, planets, nebulae, everything out there. We can know the chemistry of a star light years away. It's incredible.
It really is. So with these amazing tools in astrophysics giving us the what new branches opened up to tackle the where and when on a grand scale?
Well, the progress just kept accelerating. Better observation techniques, incredibly sensitive new detectors. Things like photoelectron multipliers, electron-optical converters, CCDs, basically superpowered digital cameras for faint light and other radiation. These boosted accuracy and sensitivity like crazy, and they let us see in different wavelengths, not just visible light.
Opening up even more of the universe.
Suddenly, distant galaxies, billions of light years away, became things we could study in detail. This explosion of data and capability led to fields like stellar astronomy, cosmology, and cosmogony.
Okay, break those down for us. They sound like the really big picture stuff.
They are. Stellar astronomy, you can sort of date its start to the 1830s when we first measured distances to stars, studies how stars are distributed in space, how they move within our galaxy, and it looks at other galaxies too, patterns and populations of stars. Then cosmology, that's the big one. It studies the origin, the structure, the evolution of the universe as a whole.
The whole shop.
The whole shebang. It relies heavily on physics, especially Einstein's general relativity, plus all the observational data we can get. It really took off in the early 20th century. And finally, cosmogony. This focuses on the origin and development of specific celestial bodies and systems, stars, planets, galaxies. Early on, like 18th, 19th century, it was mostly about how the solar system formed. But with modern physics and astrophysics, we can now seriously study how stars are born and die, and even how galaxies themselves formed back in the early universe.
Okay, so we have all these branches, all this specialization, but underlying it all, what's the core method? How do astronomers actually get the information? It's not just looking through eyepieces anymore, is it?
No, not entirely, but the fundamental method is still astronomical observation.
Yeah.
Purposeful, active registration of information coming from the universe. That's still the main source of knowledge, the empirical data. For thousands of years, it's been about precisely measuring positions, movements, brightness.
To figure out distances, sizes, the laws governing motion.
Exactly, capturing that light, that radiation, and analyzing it.
And where does this happen now? Not just on hilltops anymore, I assume.
Well, some still are on hilltops. But yes, we have specialized research institutions, astronomical observatories, built all over the world, often in remote places high up away from city lights where the air is clear and steady.
Makes sense.
And they use incredibly advanced gear. Huge telescopes to gather light, sophisticated instruments to analyze it, and massive computing power to process the data torrents. Optical telescopes still magnify, sure, but their main job now is light gathering, letting us see incredibly faint, distant objects.
But you mentioned seeing beyond visible light earlier. How do we see the invisible parts of the universe?
Right, that was another revolution. After World War II, radio technology exploded. Scientists realized they could use improved receivers, big antennas, even repurposed radar tech to detect radio waves coming from space. From the sun, but also from really distant objects.
Then that became
Radio astronomy, whole new branch of astrophysics. It opened up a completely invisible universe. We discovered things like pulsars and quasars, saw gas clouds where stars are born, things totally hidden from optical telescopes. It led to amazing discoveries.
And then the ultimate high ground, space itself. Getting instruments above the atmosphere must have changed everything again.
Oh, absolutely. Putting telescopes and instruments on spacecraft, that was transformative. Suddenly we could study wavelengths. The Earth's atmosphere completely blocks ultraviolet, X-rays, gamma rays from the sun, stars, galaxies, black holes.
Stuff we were totally blind to before.
Completely blind. These space-based observations just incredibly expanded the amount of information we could get about the physics of the universe. It was like taking off cosmic blinkers.
So we've gone on this incredible journey, from cave drawings to space telescopes. It's mind-blowing. But let's bring it back down to Earth. Beyond the sheer wonder, why does astronomy matter so much? What's its significance for us, practically speaking?
It's had huge practical impacts throughout history. But I think its main significance has always been deeper, shaping our scientific worldview, understanding our place. But the practical side is undeniable. Think about practical astronomy. Those methods for navigation are still used in shipping, aviation, and now, crucially, in space travel, in cosmonautics. Guiding probes to Mars or Jupiter requires incredibly precise star coordinates. That drives demand for better measurements of stars, quasars, pulsars.
Quasars,
Yes.
those super bright galactic cores.
Exactly.
Yeah.
They act like fixed points in the sky for navigation.
Yeah.
And as we explore the solar system more, we need detailed maps of the Moon, Mars, Venus. That's astronomy, providing the data for future missions.
And even something as basic as telling time, that's linked too, right?
Deeply linked, the official time services around the world. Their work relies on astronomical observations to keep track of Earth's rotation precisely. Modern atomic clocks are unbelievably accurate, like losing a second over tens of millions of years. That accuracy lets us study tiny changes in Earth's spin, which is essential for keeping everything synchronized: GPS, financial markets, the internet. It all relies on that precise timekeeping rooted in astronomy.
That's amazing. What about celestial mechanics? You mentioned guiding probes, but does it have applications closer to home, like finding resources?
It does, surprisingly. Studying the tiny deviations in the orbits of artificial satellites, AES, is a key task. And here's the cool part. Tiny changes in a satellite's altitude as it orbits can actually be caused by variations in the density of the rocks below it on Earth.
Seriously, gravity mapping from space.
Essentially, yes. Detecting denser areas could indicate deposits of oil, gas, or iron ore. So studying satellite orbits helps us prospect for resources on Earth.
Okay, that's a connection I never would have made. And studying other planets' atmospheres, how does looking at Venus or Mars help us here?
It gives us cosmic laboratories. Studying atmospheres on other worlds helps us understand the fundamental physics that govern our atmosphere. We could build better climate models, make more confident weather predictions. For instance, understanding Venus's runaway greenhouse effect, caused by its thick sulfur clouds. That has direct relevance to climate change studies here.
Learning from their mistakes, sort of.
Or studying Mars' global dust storms that cool its surface that helps us understand atmospheric dynamics under different conditions. It broadens our understanding immensely.
And what about astrophysics? Does studying stars and galaxies actually lead to new technologies down here?
Absolutely. It pushes the boundaries of what's possible. Studying how the sun generates energy through nuclear fusion, that directly inspired the dream of controlled thermonuclear reactors for clean energy.
Fusion power. The Holy Grail.
Indeed. Or studying solar prominences, those huge plasma eruptions. That led to ideas about using magnetic fields to contain superhot plasma, which is key for fusion, and also led to concepts like magnetohydrodynamic generators. And the Solar Service, the network, monitoring the sun's activity, its data, is used everywhere. Meteorology, space travel, even medicine, protecting astronauts and predicting impacts on power grids and communications.
It's incredible how interconnected it all is, but there's a deeper, maybe more existential side too, about Earth's place, our vulnerability.
Yes, definitely. Astronomy constantly reminds us Earth isn't isolated. We're bathed in particles and radiation from the sun, from space. And think about supernovae exploding stars. They release unimaginable energy.
How much energy?
Enough that a supernova, relatively nearby, say 60 light years away, which is close, cosmically speaking, could potentially deplete Earth's ozone layer drastically, maybe 20 times thinner. That would let in maybe 1,000,000 times more harmful UV radiation. Catastrophic for life.
That's sobering.
It is. And stellar astronomy studies how often these events happen, where the dangerous stars are. It helps us understand the potential cosmic hazards. Earth is, as far as we know, unique in hosting complex life, human civilization. If our planet is truly unique, then our responsibility to preserve it is immense. Astronomy helps us grasp that context, that fragility.
What a journey. Seriously, from ancient cave drawings, wondering about lights in the sky, all the way to space telescopes studying exploding stars and pondering our own survival, astronomy really captures that relentless human curiosity.
It really does, and this deep dive, based on the sources you provided, shows just how tangled up our understanding of the cosmos is with our daily lives, our technology, even our future as a species. It underlines that knowing about the universe isn't just some academic exercise. It fundamentally shapes our worldview, and it has very real consequences.
So maybe the biggest takeaway for you listening is this. Looking up isn't just about discovery out there, it's also about understanding our own unique, maybe fragile place right here, and the responsibility that comes with that knowledge. Thank you again for providing the sources that made this deep dive possible. We really hope digging into them like this has been valuable for you. Keep exploring, keep asking questions. Until next time, keep looking up.